On January 19th, 2026, something touched Earth that wasn't supposed to reach us. Not with that speed, not with that force. A solar storm traveling at over 1,000 kilometers per second compressed our planet's magnetic shield so violently that satellites found themselves exposed to raw space. And then, exactly during peak magnetospheric chaos, the ground beneath California's San Andreas Fault moved. Scientists are calling it coincidence. The data is calling it something else entirely. Because buried in ancient tree rings and ice cores is evidence of a 12,000-year rhythm, a pattern of solar violence our civilization has never witnessed, but Earth remembers in isotopic scars. Stay until the end, because what happened in January might not be the storm itself. It might be the warning. Subscribe and follow along as magnetometers continue recording and satellite telemetry keeps streaming in, because what we learn from analyzing the January storm over the coming months will either confirm it was just an unusually intense but isolated event, or reveal that we've been systematically missing the connections between solar violence, weakening magnetic shields, and the kind of planetary scale disruptions that only show up in geological records we haven't been reading carefully enough. Something happened on January 19th, 2026 that wasn't supposed to be possible. Not according to our models. Not according to the physics we've spent decades mapping. And definitely not according to the comfortable assumptions we've built our entire space weather forecasting system upon. The sun threw a tantrum, and Earth took the hit. But calling it a solar storm feels inadequate, like calling a tsunami a wave. This was an S4 level geomagnetic event, a classification reserved for incidents that makes scientists quietly update their risk assessments, and engineers nervously check satellite telemetry. The coronal mass ejection screamed toward us at over 1,000 kilometers per second, carrying a payload of magnetized plasma dense enough to make our planet's protective bubble buckle inward like a crushed aluminum can. Here's where it gets interesting. CMEs that fast usually burn themselves out quickly. They're sprinters, not marathon runners. The velocity comes from explosive magnetic reconnection in the sun's corona, a violent snapping of field lines that flings billions of tons of matter into space. But this storm didn't just sprint. It maintained that terrifying speed across 93 million miles of empty space, arriving at Earth's doorstep in roughly 30 hours. For context, the average CME takes 3 to 4 days to make that journey. This thing covered the distance in the time it takes to binge watch a season of television. The 30-hour transit time is what makes veteran space physicists go quiet. It places this storm in the same velocity class as the Carrington event of 1859 and the near-miss superstorm of 1972. These are the events we talk about in cautious hypotheticals, the ones that occurred before we had a fragile shell of satellites and a power grid vulnerable enough to cascade into continent-wide blackouts. But speed alone doesn't tell the whole story. This CME arrived with structural coherence that shouldn't have survived the trip. The magnetic field embedded in the plasma, what scientists call the interplanetary magnetic field, or IMF, measured over 60 nanoteslas at Earth. To put that in perspective, a typical geomagnetic storm might clock in at 20 to 30 nanoteslas. This was double that. The density was equally absurd, like the storm had packed for a longer trip and brought extra mass just to make a point. When this wall of magnetized material slammed into Earth's magnetosphere, something rare happened. The boundary that normally sits about 60,000 kilometers above Earth's surface, a safe distance well beyond the orbit of our most precious satellites, compressed inward. Way inward. Geosynchronous orbit, where communication satellites circle at roughly 35,000 kilometers up, suddenly found itself outside the protective bubble. Satellites that had spent decades in a relatively safe cosmic harbor were abruptly exposed to the full fury of solar wind and radiation. Engineers monitoring those satellites reported what you might expect: charging events, sensor anomalies, magnetometers pegging at maximum scale. The kind of telemetry that makes you reach for the manual on how to safe mode a billion-dollar asset before it becomes expensive debris. But here's the twist that nobody saw coming. The storm arrived with its magnetic field oriented northward. And in the strange physics of space weather, that should have been a relief. When a CME's magnetic field points south, it couples efficiently with Earth's northward pointing field, like two magnets attracting. That's when you get the spectacular auroras, the dancing green curtains that tourists flock to Norway and Iceland to witness. Southward fields dump energy into our upper atmosphere, ionizing particles, lighting up the sky in luminous displays that are as beautiful as they are scientifically informative. This storm's field pointed north, same polarity as Earth's. That should have meant less coupling, less energy transfer, less of a show. The auroras should have been spectacular given the storm's intensity. Instead, they were strangely muted. People at high latitudes reported seeing lights, yes, but nothing that matched the ferocity suggested by the satellite data. It was like watching a fireworks finale where half the shells failed to ignite. So, where did the energy go? That's the question that should keep you up at night. Energy doesn't just disappear, it transforms, it redistributes. And when several quintillion joules of magnetic and kinetic energy don't radiate away as pretty lights in the ionosphere, they have to go somewhere else. Space weather logs from that day are filled with quiet anomalies. Not the dramatic headline-grabbing failures, but the subtle weirdness that scientists notice when they review data months later. Magnetometers on the ground registered spikes that didn't correlate with auroral activity. Ground-induced currents, the electric rivers that flow through Earth's crust during geomagnetic storms, showed unusual patterns: deeper penetration, longer duration, higher amplitude in regions that normally register as magnetically quiet. This wasn't just a big storm. This was a storm that broke several independent baseline assumptions simultaneously. It was too fast, too dense, too coherent, and too energetically misrouted to fit comfortably into the statistical distribution of events we've observed over the past 70 years of space-age monitoring. And here's what makes this more than an academic curiosity. We've only been watching the sun with modern instruments since the 1950s. 70 years. The sun is 4.6 billion years old. We've observed it for roughly 0.0000015% of its lifetime. Calling our dataset comprehensive is like watching someone for 3 seconds and claiming you understand their entire personality. This storm is a baseline breaker, not an outlier to be dismissed, but a data point that suggests our baselines were drawn in the wrong place to begin with. It's the kind of event that makes you wonder what else we've been systematically underestimating, because our observational window is so laughably narrow. But the storm itself, as anomalous as it was, might not even be the most disturbing part of this story. Because while satellites were getting hammered, and magnetometers were screaming, and scientists were frantically modeling the magnetospheric response, something else happened. Something on the ground. Something that raises questions nobody in the mainstream scientific community wants to touch with a 10-foot pole. If the energy didn't light up the sky, where exactly did it go instead? During the peak hours of magnetospheric compression, while Earth's magnetic shield was being crushed inward and ground-induced currents were surging through the crust with unusual intensity, the ground moved. Specifically, it moved in Indio, California, roughly 20 miles northeast of Palm Springs, at a depth of about 3 kilometers beneath one of the most seismically sensitive fault zones on the planet. Magnitude 4.9. Not huge by California standards, but absolutely not small either. Strong enough to rattle windows, knock items off shelves, and send thousands of smartphone alerts screaming into the pockets of residents who've grown uncomfortably accustomed to the Earth occasionally reminding them, it's alive. The quake hit on January 10th, 2026, at a timestamp that overlaps almost perfectly with the maximum compression of Earth's magnetosphere. Timing. 3 kilometers deep, San Andreas fault system, during a historic geomagnetic storm. Let's talk about why this is difficult to dismiss. Earthquake depth matters more than most people realize. Shallow quakes, those occurring in the top 5 kilometers of crust, are exquisitely sensitive to stress changes. And I mean small stress changes. Research has shown that tidal forces from the moon, which alter crustal stress by fractions of a bar, can nudge faults already near failure over the edge. If lunar gravity can do it, what can a massive injection of electrical current into the crust accomplish? Telluric currents. That's the term for the electrical rivers that flow through Earth during geomagnetic storms. When the magnetosphere gets slammed and starts fluctuating wildly, it induces electric fields in the conductive layers of our planet. These aren't trivial currents. They're strong enough to trip circuit breakers in power grids, corrode pipelines, and interfere with railway signaling systems. They flow along paths of least resistance, which often means following fault zones where fractured rock and groundwater create conductive channels. California's geology is practically an electrical highway. The San Andreas fault system isn't just a crack in the ground. It's a complex, three-dimensional zone of fractured rock, mineral-rich fluids, and stress concentrations that have been building for centuries. The entire region is a patchwork of conductive pathways, and during a geomagnetic storm, those pathways light up with induced current. Now, here's the uncomfortable part. Faults don't need much encouragement when they're already loaded with tectonic stress. The San Andreas has been locked and loaded for decades. Everyone knows the big one is coming. The only question is when. What happens when you add a sudden, intense electromagnetic stress to a fault system already teetering on the edge of failure? Mainstream seismology will tell you, correctly, that correlation does not equal causation. Just because two things happen at the same time doesn't mean one caused the other. Fair enough. Science demands rigor, but correlation also doesn't equal irrelevance. When a statistically rare geomagnetic event coincides with seismic activity in a critically stressed fault zone, pretending there's nothing worth investigating is intellectually dishonest. And this wasn't just one quake. The Indio event triggered a swarm. Dozens of smaller quakes followed in the hours and days after, ranging from magnitude 2 to 3.5. Swarms are weird. They don't follow the typical aftershock decay pattern you'd expect from a main shock aftershock sequence. Instead, they cluster and migrate, suggesting ongoing stress redistribution in the fault system. It's like the crust is still settling, still responding to whatever perturbation kicked things off. There's a reason this connection isn't being shouted from the rooftops of university geology departments. Solar seismic correlations are reputationally dangerous. Suggest that the sun might influence earthquakes, and you risk being lumped in with the pseudoscience crowd, the people predicting quakes based on planetary alignments and YouTube conspiracy videos. Scientists have careers to protect, grants to secure, and peer reviewers to satisfy. Exploring fringe correlations is a quick way to tank your credibility, but the data doesn't care about reputations. And quietly, behind closed doors and in carefully worded conference presentations, some researchers are asking whether external electromagnetic forcing might act as a trigger, not a cause, for seismic events. The distinction matters. Nobody's claiming the sun creates tectonic stress. That comes from plate tectonics, from the slow, grinding collision of crustal slabs. But once that stress is built up, once a fault is primed and ready to slip, could an external perturbation provide the final nudge? Think of it like a boulder balanced on a hillside. Gravity and friction have it locked in place, but barely. A stiff breeze won't move it, but a precisely timed shove, even a small one, might be enough to send it tumbling. Telluric currents could be that shove. They alter pore pressure in fault zones. They change the electrical potential across fracture surfaces. They introduce a variable that wasn't part of the original tectonic equation. This is a natural experiment humanity didn't design and can't replicate. We can't exactly fire controlled bursts of geomagnetic energy at fault zones to test the hypothesis. Ethics and practicality both say no. So we're left with observational data, with correlations that are suggestive but not conclusive, with questions that make people uncomfortable because the implications are enormous. Here's the thought that should genuinely unnerve you. The January storm had a northward magnetic field orientation. It was, by conventional metrics, less geo-effective than it could have been. If that same CME had arrived with a southward field, the energy coupling would have been far more intense. The ground-induced currents would have been stronger. The magnetospheric compression would have lasted longer. Would the seismic response have been different? Would we have seen larger quakes, more swarms, activity along multiple fault systems instead of just one? We don't know. We can't know. But the question hangs there, impossible to ignore. And it raises an even bigger question. Has this happened before? Not just a correlation between a solar storm and a single earthquake, but a pattern of solar activity coinciding with periods of intense seismic and volcanic unrest on a planetary scale. Have we seen this before, on a much larger and more catastrophic level, and simply forgotten because it happened too long ago to leave written records? Humans have been keeping written records for roughly 5,000 years. Before that, history fades into oral tradition, myth, and archaeological fragments. But Earth keeps its own records, written in layers of ice, sediment, and the annual growth rings of ancient trees. And those records are telling us something disturbing about the sun's behavior over timescales we're only beginning to appreciate. Tree rings aren't just pretty patterns, they're time capsules. Each ring represents 1 year of growth, and trapped within that wood are isotopes created by cosmic radiation bombarding Earth's atmosphere. Specifically, carbon-14 and beryllium-10. Under normal conditions, these isotopes accumulate at a steady background rate, created when cosmic rays strike nitrogen and oxygen atoms in the upper atmosphere. But occasionally, the concentrations spike dramatically. Scientists have found several of these spikes in the tree ring record, sharp increases in radioisotope production that can't be explained by normal solar activity or gradual variations in Earth's magnetic field. The most famous are the Miyake events, named after physicist Fusa Miyake, who first identified them. The biggest known spike occurred around 774 to 775 AD. Another happened around 993 AD. And when researchers looked further back, deeper into the record, they found more. Around 12,850 years ago, right at the beginning of the Younger Dryas period, isotope levels jumped. Then again, around 11,600 years ago, near the end of that same climate anomaly. The timing is uncomfortably precise. These aren't vague correlations spread across millennia. These are sharp, well-defined events clustering around periods of massive environmental upheaval. The Younger Dryas is one of the strangest chapters in Earth's recent climate history. For context, the planet had been warming steadily as the last ice age wound down. Glaciers were retreating, sea levels were rising, life was recovering. Then, suddenly, temperatures plunged, not gradually, but catastrophically fast. Within a few decades, maybe less, the climate flipped back into near glacial conditions. Megafauna went extinct. Human populations crashed. The archaeological record shows a clear break, a before and after that marks one of the most significant disruptions in human prehistory. What caused it? The mainstream explanation involves a disruption of ocean currents, specifically the Atlantic meridional overturning circulation, triggered by massive freshwater pulses from melting glaciers. That might be part of the story, but it doesn't fully explain the global synchronicity of the event, the fact that climate chaos erupted simultaneously across multiple continents. And it definitely doesn't explain the radioisotope spikes. Miyake events are absurdly powerful. The 774 AD event increased carbon-14 production by roughly 1.2% in a single year. That requires an influx of cosmic radiation or solar protons orders of magnitude beyond anything we've observed in the modern era. The largest solar flare ever recorded, the 1959 event, doesn't come close. We're talking about energy releases that make contemporary solar storms look like firecrackers next to a thermonuclear detonation. And here's what keeps me up at night. These events aren't random, they cluster. Roughly every 1,000 to 1,500 years, we see isotope spikes that suggest the sun went into some kind of hyperactive mode. And when you zoom out even further, to the 10,000 to 12,000 year scale, the clustering becomes even more apparent. It's not a perfect cycle, it's not clockwork, but it's also not random noise. There's a rhythm here, a pattern of solar behavior that operates on timescales far longer than our brief observational window. The January 2026 storm, as intense as it was, barely registers compared to a true Miyake event. If that storm was a warning shot, a Miyake event is the full broadside. But here's the thing about complex systems. They often announce themselves before the main event. Seismologists talk about foreshocks, the smaller quakes that precede a major rupture. Volcanologists watch for precursory tremors and gas emissions before an eruption. Could we be seeing something similar with solar activity? The sun has been unusually active in recent years. Solar cycle 25 is exceeding predictions, producing more sunspots, more flares, more CMEs than models anticipated. Scientists keep revising their forecasts upward, surprised by the intensity and frequency of events. And our magnetic field, the shield that protects us from solar fury, is weakening. Not uniformly, but in patches and swaths that create vulnerable zones where radiation and charged particles can penetrate deeper than they should. The South Atlantic anomaly, a region where the magnetic field has weakened significantly, is expanding. The North Magnetic Pole is racing towards Siberia at speeds that have accelerated dramatically in recent decades. The overall field strength has dropped roughly 10% over the last century and a half. These aren't apocalyptic changes, but they're directional. They're trends. And when you combine a more active sun with a weakening magnetic shield, you create conditions that might not have existed for thousands of years. Geomagnetic excursions are periods when the magnetic field weakens dramatically, sometimes flipping polarity partially or completely before restabilizing. The last full reversal was 780,000 years ago, but excursions, temporary weakening events, happen more frequently. And guess what overlaps with the Younger Dryas? The Gothenburg magnetic excursion, a period of significantly reduced field strength and chaotic field geometry. Reduced shielding plus intense solar activity equals a very bad time for anything living on the surface. Cosmic radiation increases. Atmospheric chemistry changes. Ozone depletion accelerates. The protective bubble that has allowed complex life to flourish on land gets perforated, letting in wavelengths and particles that DNA really doesn't appreciate. So we have isotope spikes indicating massive solar events. We have geomagnetic excursions indicating a weakened shield. We have climate catastrophes and extinction events clustered around the same time windows. And we have a modern solar storm that, while nowhere near Miyake scale, still managed to do things that surprise scientists and possibly nudge a major fault system while it was at it. Pattern recognition is a double-edged sword. Humans are wired to see patterns even in random noise, but we're also capable of missing real patterns because they operate on scales we're not cognitively equipped to perceive. 12,000 years is nothing to Earth. It's a geological eye blink. But to human civilization, it's prehistory. It's myth. It's the kind of timescale we don't plan for because we have no institutional memory of it. If these events follow a rhythm, even a loose one, we're overdue for the next major pulse. Not tomorrow, not next year, But on the timescales that matter to planetary processes, we might be entering a danger zone we don't fully recognize. Because the last time it happened, we were still figuring out agriculture and hadn't invented writing yet. What protects us during these periods? Or more accurately, what fails to protect us when the shield weakens and the sun decides to remind us it's a star capable of violence on scales we've only theorized about? Earth's magnetic field is not a static shield. It's a dynamic, roiling structure generated by the motion of molten iron in the outer core, roughly 3,000 kilometers beneath your feet. This geodynamo has been running for billions of years, creating the protective bubble that deflects solar wind and cosmic radiation, making the surface of our planet habitable for complex life. But it's not consistent. It fluctuates. It wanders. And right now, it's doing something that makes geophysicists very, very interested. The field strength is declining. Not everywhere uniformly, but in specific regions that create patchwork vulnerabilities. The South Atlantic anomaly is the poster child for this phenomenon. Over a vast stretch of ocean and parts of South America and Southern Africa, the magnetic field has weakened to roughly 60% of its global average. Satellites passing through this region experience higher radiation doses, occasional bit flips in their electronics, and accelerated degradation of sensitive components. The International Space Station has to shut down non-essential systems when transiting the anomaly to avoid damage. This isn't new. The anomaly has existed for decades, but it's growing, both in area and in intensity, or rather, in weakness. The field is thinning, creating a larger window through which charged particles can penetrate deeper into the atmosphere. And it's not alone. Smaller weak spots are appearing at other latitudes, suggesting that the overall field geometry is becoming more chaotic, less stable. The North Magnetic Pole, meanwhile, is in a hurry. For most of recorded history, it wandered slowly around the Canadian Arctic at a leisurely pace of about 10 to 15 kilometers per year. Then, in the 1990s, it started accelerating. By the early 2000s, it was moving at 50 kilometers per year. Now, it's racing towards Siberia at speeds approaching 60 kilometers annually. That's not normal. That's not the behavior of a stable field configuration. Magnetic pole movement is driven by changes in the flow patterns of molten iron deep in the core. It's chaos down there. Turbulent convection driven by heat and rotation. And the magnetic field we measure at the surface is just the aggregate result of countless swirling currents. When those currents shift, the field shifts. And right now, the currents appear to be reorganizing in ways that could precede an excursion or even a full reversal. Reversals take thousands of years. The field doesn't just flip overnight. It weakens gradually, becomes multipolar with several north and south poles scattered around the planet, then eventually settles into a new configuration. During the transition, the field strength drops significantly, sometimes to as low as 10% of normal. That's when things get interesting. And by interesting, I mean potentially catastrophic for anything relying on that shield. But let's talk about something nobody's quite sure how to model yet. The Arctic Ocean, specifically the region around the Gackle Ridge. This is a mid-ocean spreading ridge buried beneath Arctic ice, one of the slowest spreading and most volcanically active ridges on Earth. It's a massive fracture in the crust, where magma wells up from the mantle, creating new ocean floor and releasing enormous amounts of heat and dissolved minerals into the frigid water above. The Gackle Ridge is also highly conductive. Magma, hot rock, and mineralized seawater create electrical pathways that could, hypothetically, interact with the magnetic field in ways we're only beginning to explore. Some researchers have speculated, and I emphasize speculated, that interactions between the weakening magnetic field and conductive structures in the crust could create feedback loops. Changes in the field alter current flows in the crust and oceans. Those current flows, in turn, influence the geodynamo. It's a coupled system, and coupled systems can do strange things when perturbed. We don't know if this is happening. We don't have the data to prove it, but the timing is suggestive. The North Magnetic Pole is accelerating toward Siberia, which places it increasingly over or near the Gackel Ridge and the conductive pathways of the Arctic Ocean basin. Coincidence? Probably, but maybe not. What we do know is that modern civilization has made Earth electrically leakier. Power grids, pipelines, communication cables, railways, all of these create conductive pathways that didn't exist 150 years ago. We've wrapped the planet in a metal spiderweb, and during geomagnetic storms, that web lights up with induced currents. Transformers blow, pipelines corrode, GPS systems glitch. The 1989 Quebec blackout was caused by a relatively moderate geomagnetic storm. A Carrington-level event today would be orders of magnitude worse. Satellites are even more vulnerable. We have thousands of them now, forming the backbone of modern communication, navigation, weather forecasting, financial transactions, and military operations. Geosynchronous orbit, where the most valuable assets live, used to be considered safe. Far enough out to avoid the worst of atmospheric drag, but still inside the magnetosphere's protective bubble. The January storm pushed the magnetopause inside that bubble. For hours, those satellites were exposed. They survived, but the margin was narrower than anyone wants to admit. Forecasting helps, but only if you have time. CMEs take hours to days to reach Earth, giving operators a window to prepare. But the forecasting models are built on decades of data from a relatively quiet sun during a period of relatively strong magnetic shielding. If the sun ramps up and the shield weakens further, we're extrapolating into a regime we've never actually observed. The models might hold, or they might fail spectacularly, giving us false confidence, right up until the moment the grid goes dark. Magnetospheric compression used to be a rare event, the kind of thing that happened once or twice a solar cycle. Now it's becoming more common, and the compressions are lasting longer. That's not because the sun is necessarily more active than it was centuries ago. It's because our shield is weaker, more easily deformed, more prone to letting energy through. We're running a stress test we didn't sign up for. Every major geomagnetic storm is probing the system, finding weak points, revealing vulnerabilities that weren't obvious during calmer times. And the uncomfortable reality is that we don't know where the breaking point is. We don't know how much worse the shielding has to get, or how intense a storm has to be before we cross a threshold from inconvenient disruptions to civilization-altering catastrophe. The January storm was a medium-sized hammer hitting a weakening wall. The wall held, but it flexed in ways it shouldn't have. And if the hammer gets bigger, or the wall gets weaker, what happens when something finally gives? What kind of event would it take to overwhelm our defenses entirely? And would we recognize it before it arrived, or only in hindsight after the damage was already done? Let's be clear up front. Nobody knows for certain what causes Miyake events. We have hypotheses, educated guesses, based on incomplete data from events that happened centuries or millennia ago. What we do know is that something injected massive amounts of high-energy particles into Earth's atmosphere, enough to create isotope spikes visible in tree rings and ice cores across the planet. The question is what? The leading candidate is a solar superflare. Our sun is capable of flares far more powerful than anything we've observed in the modern era. We know this because we've watched other sun-like stars throw tantrums that dwarf our worst nightmares. A superflare from our sun could theoretically blast Earth with a proton flux intense enough to explain the isotope spikes. The problem is, we've never actually seen our sun do this. Not in 400 years of telescopic observation. Not in 70 years of space-age monitoring. Either we've been extraordinarily lucky, or these events are vanishingly rare. Option 2 is a cosmic ray jet. Maybe a nearby supernova or some other stellar cataclysm sent a focused beam of radiation our way. This hypothesis struggles with geometry. A supernova close enough to affect us this dramatically would leave other signatures. We'd see remnants, chemical anomalies in the geological record, maybe even crater evidence from meteorite bombardment. The isotope spikes are strong, but they're not accompanied by the kind of apocalyptic devastation you'd expect from a close-range supernova. So this explanation doesn't quite fit either. Then there are the more speculative ideas, the ones that make mainstream scientists uncomfortable but refuse to go away because the data keeps not fitting into neat boxes. What if the sun and Earth are electrically coupled in ways we don't fully understand? What if, during periods of extreme solar activity combined with weakened magnetic shielding, a discharge occurs between the sun's extended plasma environment and Earth's ionosphere? This is deep into alternative model territory, the realm of electric universe proponents and researchers who argue that electromagnetic forces play a much larger role in solar system dynamics than conventional models admit. I'm not advocating for these ideas. I'm pointing out that when none of the conventional explanations fully account for the data, unconventional models start looking less crazy. Consider what we observed in the January storm. Energy that should have dissipated as auroras apparently didn't. Magnetospheric compression that pushed satellites into exposed zones. Ground-induced currents that possibly triggered seismic activity. What if, under the right conditions, energy from a solar storm doesn't just interact with our atmosphere and magnetosphere, but couples directly into Earth's interior? The planet is not electrically neutral. The crust, mantle, and core all have distinct electrical properties. Conductivity varies with temperature, mineral composition, and the presence of fluids. During a massive geomagnetic storm, telluric currents flow through the most conductive pathways. Normally, these are minor perturbations, measurable but inconsequential. But scale up the energy input by several orders of magnitude, add a weakened magnetic shield that allows deeper penetration, and you might create conditions for electrical discharge or resonance effects that we've never witnessed in the modern era. I want to be absolutely clear. This is speculation. This is not established science. But it's speculation grounded in the recognition that our current models don't fully explain Miyake events, and dismissing alternatives without investigation is how science stagnates. Another possibility is that Miyake events represent a state change in the sun itself, a temporary shift into a more energetic mode of operation. Stars aren't static. They evolve over billions of years, yes, but they also fluctuate on shorter timescales, driven by magnetic field dynamics, convection patterns, and mechanisms we're still trying to understand. Our sun might have operational modes we simply haven't observed because we haven't been watching long enough. The frustrating thing about rare, high-impact events is that they're almost impossible to predict or prepare for when you don't understand the mechanism. Earthquake prediction fails because we don't fully understand fault mechanics. Hurricane intensity forecasting improves every year, but still has significant error bars because atmosphere-ocean coupling is fiendishly complex. Solar physics is even worse because we can't exactly install sensors inside the sun or run controlled experiments. What we can do is look at the patterns. Miyake events cluster. They're not evenly distributed through time. That clustering suggests a mechanism with periodicity, even if it's not a strict cycle. And the clustering appears to correlate, loosely but disturbingly, with periods of geomagnetic instability and climate disruption. The Younger Dryas isotope spikes occurred during a geomagnetic excursion. The 774 AD event happened during a period of rapid climate change and societal collapse across multiple civilizations. The 993 AD event coincides with historical records of unusual auroras and possible crop failures in Europe and Asia. These aren't smoking guns. They're circumstantial evidence that something connects solar activity, magnetic field behavior, and planetary scale disruption. Mainstream science treats these correlations cautiously, and rightly so. Correlation hunting without rigorous statistical analysis leads to false positives and conspiracy theories. But the flip side is that excessive caution can blind us to real patterns, especially when those patterns operate on timescales longer than individual careers or institutional memory. Here's the deeply uncomfortable truth. If Miyake events follow a rhythm, even a loose one, and if that rhythm operates on timescales of thousands of years, we have no way of knowing where we are in the cycle based on modern observations alone. We're building risk models on 70 years of data, trying to predict events that happen every millennium or so. It's like watching the weather for a single afternoon and trying to forecast the next ice age. The January storm gave us a data point. A small one, comparatively speaking, but a modern measurement of an S4 level event during a period of weakening magnetic shielding. It behaved in ways that surprised scientists. It possibly triggered seismic activity. It compressed the magnetosphere inside geosynchronous orbit. It did all of this with a northward magnetic field, which should have limited its effectiveness. Now imagine a Miyake scale event. 10 times the energy. 100 times. A southward field orientation that couples perfectly with Earth's magnetic environment. A shield already weakened to 50% of normal. What happens then? Not just to satellites and power grids, but to the planet itself, to the crust, the oceans, the atmosphere, the biosphere? We don't know, and the fact that we don't know, that we can't even confidently explain what happened 12,000 years ago, should bother us more than it does. Are we seeing the early stages of something similar? Is the sun warming up, cycling into a more active phase that operates on timescales we don't track? Or is January 2026 just noise, a random fluctuation that means nothing in the grand scheme? The only way to know is to keep watching, to keep measuring, and to hope that if the pattern is real, we recognize it in time to do something other than document our own surprise. For decades, astronomers have been watching other stars, cataloging their flares, mapping their magnetic cycles, trying to understand if our sun is typical or an outlier. The data collected is vast. Millions of stars observed by missions like Kepler and TESS, each one monitored for brightness variations that could indicate flares, transits, or other stellar activity. Too much data for humans to analyze comprehensively. That's where machine learning comes in. Recent studies using AI to sift through stellar flare data have found something unsettling. Sun-like stars, the ones we thought were relatively calm and predictable, occasionally throw superflares. Not often, not regularly. But when they do, the energy release is staggering, orders of magnitude beyond the largest flares we've recorded from our own sun. These events show up as sudden, extreme brightness spikes in the light curves, followed by gradual decay over hours or days. The AI doesn't just find individual events, it finds patterns, clustering, non-random distributions that suggest superflares aren't purely stochastic, but influenced by underlying stellar dynamics that operate on longer timescales than human observation windows. The algorithms detect correlations between magnetic field complexity, rotation rate, and flare intensity that human analysts had missed because the patterns are buried in noise and require analyzing thousands of stars simultaneously to emerge. Here's the problem: observation bias. We've been watching these stars for years, maybe decades in some cases. That sounds like a lot until you remember that stars live for billions of years. If a sun-like star throws a superflare once every 1,000 years, and we've watched it for 20 years, we'll probably miss it. Our sample is biased toward calm periods, simply because calm is statistically more common, and catastrophic events are rare. But rare doesn't mean impossible, and rare on human timescales might be routine on stellar timescales. A 1,000-year event happens, on average, 10,000 times over the 10 billion year lifespan of a sun-like star. That's not rare. That's just in the rhythm of stellar evolution, a periodic tantrum that any star might throw when conditions align. The numbers are sobering when you think about them. The Kepler mission alone monitored over 150,000 stars continuously for years. TESS has observed hundreds of thousands more. Each star is a laboratory, an independent experiment in stellar physics running parallel to our own sun's evolution. When you aggregate that much data, statistical patterns emerge that would be invisible in any single star's behavior. The machine learning algorithms aren't magic. They're just very, very good at spotting correlations across massive datasets that no human could hold in their head simultaneously. What the AI found is that superflares on sun-like stars follow power law distributions, the same mathematical pattern that describes earthquakes, forest fires, and stock market crashes. Most flares are small. Moderate flares are less common. Huge flares are rare. But the tail of that distribution extends much further than we'd previously recognized. The really catastrophic events, the ones that would qualify as Miyake scale if they hit Earth, exist in the data. They're just sparse enough that human analysts looking at individual stars miss the pattern. The AI analysis suggests that our risk estimates for solar superflares are probably too low. We've assumed, based on limited data, that events like Miyake spikes are extraordinarily rare, once in 10,000 years or longer. But if sun-like stars routinely produce superflares when observed over long enough periods, and if our sun is indeed typical, then maybe these events happen more often than we think. Maybe every 500 years. Maybe every 1,000. Maybe we're just in a lucky stretch where none have occurred during recorded history. Think about what that means. Recorded history, generously defined, goes back maybe 5,000 years. Writing systems, organized states, the kind of record-keeping that would preserve memory of a catastrophic solar event. 5,000 years sounds like forever in human terms. It's nothing in astronomical terms. If superflares occur every 1,000 years on average, we might have missed 4 or 5 of them simply because they happened before anyone was writing things down. Or they happened, were recorded as divine omens or apocalyptic events, and the connection to the sun was lost in translation across millennia of myth and distortion. Machine learning is also finding temporal clustering in stellar activity. Stars don't flare randomly. They go through active and quiet phases, and the transitions between phases sometimes correlate with larger, more energetic events. It's like the star is building up magnetic stress, releasing it gradually through smaller flares, until something triggers a catastrophic release that dwarfs everything else. Sound familiar? It should. That's exactly how earthquakes work. Stress builds along a fault. Small quakes release some of it. But eventually, the accumulated stress exceeds the fault's strength, and you get the big one. If stars operate on similar principles, governed by magnetic stress accumulation and release, then we should expect periods of elevated activity punctuated by rare but devastating superflares. The parallel to seismology is more than metaphorical. Both systems involve complex, nonlinear dynamics where energy builds up gradually and releases catastrophically. Both systems show precursory signals that are only obvious in hindsight. Both systems have fundamental unpredictability at the event level, but statistical predictability over longer timescales. You can't predict the next earthquake, but you can estimate the probability of a magnitude 7 event in the next 50 years. Same with solar flares. We can't predict the next superflare, but we can estimate the probability that our sun will throw one in the next few centuries. The AI isn't predicting when our sun will throw a superflare. It can't. The data doesn't extend far enough back, and the physics aren't deterministic enough. But it's telling us that the probability is non-zero, possibly higher than we've been assuming, and that we should be prepared for the possibility that our relatively quiet sun might not stay quiet forever. This connects back to the tree ring isotopes and the Miyake events. If those events were solar superflares, And if superflares occur on roughly millennial timescales, then we're not dealing with one-off freak accidents. We're dealing with a feature of solar behavior that our civilization has simply never experienced because we've existed, in organized form, for a time span shorter than the recurrence interval. It's like living on a floodplain and assuming floods don't happen because there hasn't been one in living memory. The river disagrees. It floods. It just does so on timescales that exceed human institutional memory, and when it does, everyone acts surprised, even though the geological record clearly shows previous high water marks. The geological analogy extends further. Flood geologists can look at sediment layers and calculate how high the water rose during past floods. They can estimate recurrence intervals based on deposits. They can build probabilistic models that account for century-scale and millennium-scale events, not just the floods that happened in the last 30 years. Solar physics is trying to do the same thing with isotope records and AI analysis of stellar populations. We're building a geological scale understanding of solar behavior using proxies and analogs because we can't directly observe our sun over thousands of years. The AI findings are a pattern amplifier. They're not telling us anything definitively, but they're highlighting correlations and distributions that suggest we've been underestimating tail risks. Low probability, high impact events are exactly the kind of thing humans are terrible at planning for, because they don't happen often enough to feel urgent. But when they do happen, the consequences are civilization altering. We're watching the sun with better instruments than ever before. We're monitoring space weather in real time. We're building models and forecasts and early warning systems. All of this is good. But if the AI analysis is correct, and if our sun is capable of Miyake-scale events on timescales of centuries to millennia, then our 70 years of modern observation is not enough to characterize the full range of possible behavior. The instruments we've deployed are impressive. Solar observatories in space and on the ground. Magnetometers scattered across continents. Satellites monitoring the solar wind in real time. We can see sunspots forming, track CMEs as they erupt, and model their trajectories with increasing accuracy. But all of this sophisticated monitoring has only captured a narrow slice of solar behavior. It's like trying to understand Earth's climate by watching the weather for a single season. You'll learn something, but you'll miss the hurricanes, the droughts, the once-in-a-century heat waves that define the extremes of the system. What else are we missing? What other patterns exist in the data that only become visible when you analyze thousands of stars over decades and let machine learning find the correlations we can't see? And critically, what happens when one of those patterns suggests that rare events might not be as rare as we hope? The disturbing possibility is that we're living through a period of exceptional solar calm, and our entire risk framework is calibrated to this anomalously quiet baseline. If the AI is right, if sun-like stars regularly produce superflares that dwarf anything in our observational record, then we're not just underestimating risk by a little, we're underestimating it by orders of magnitude. If our metrics are wrong, if our baseline assumptions are drawn from an unrepresentatively calm sample, what are we missing right now? What signals exist in the current solar data that we're not recognizing because we don't know what to look for? The January storm surprised scientists, not because it was unprecedentedly large, but because it behaved in ways that didn't fit standard models. Energy went missing. Magnetospheric compression exceeded predictions. Possible seismic coupling occurred when it shouldn't have. Those surprises might be hints. Small deviations from expected behavior that suggest our models are missing something fundamental. The AI looking at other stars is telling us that extreme events happen more often than we think. The isotope record is telling us that Earth has been hit by these events before. The January storm is telling us that even moderate events can do unexpected things, when conditions align in ways we haven't fully characterized. We're piecing together a picture from fragments, stellar observations, geological proxies, modern measurements, machine learning analysis. None of it gives us certainty, but together, they're pointing in a direction that's hard to ignore. Our sun is capable of more than we've seen. The timing might follow patterns we're only beginning to recognize, and our current defenses, both technological and magnetic, might not be adequate for the extremes the system can produce. The AI has given us a tool for seeing patterns across scales we couldn't access before. The question is whether we'll listen to what it's showing us, or whether we'll dismiss the findings as statistical artifacts and continue assuming that our brief, calm observational window represents the full range of possibilities. Because if we're wrong about that assumption, the cost of that error won't be measured in failed satellites or power outages. It'll be measured in the resilience of civilization itself when faced with an event we convinced ourselves was too rare to prepare for. Auroras are beautiful. They're scientifically informative. They're also deeply misleading as a metric for danger. We've trained ourselves to equate spectacular light shows with geomagnetic severity, and that's a mistake. The January storm should have taught us that. Muted auroras, record magnetospheric compression, possible seismic triggering. The energy didn't go where we expected it to go, and that mismatch is more important than any photograph of green curtains dancing over Iceland. What we should be measuring is grid noise, satellite charging events, ground-induced current density, seismic response in tectonically active regions, pipeline corrosion rates, GPS timing errors. These are the canaries in the coal mine, the indicators that tell us energy is coupling into systems we depend on in ways that can cascade into failures. A transformer blown in Quebec is more significant than 1,000 aurora photos. A satellite fried in geosynchronous orbit is a louder alarm bell than a auroral oval expansion. An earthquake swarm on a major fault system during peak geomagnetic activity is a data point we cannot afford to dismiss as coincidence without thorough investigation. The January 2026 storm was a baseline shift, not an anomaly, not an outlier. A new data point that redefines what we should consider normal for an S4 event during a period of weakening magnetic shielding. If this is the new normal, what does an S5 look like? What about a Miyake event, which would blow past the entire classification scale we've built? Let me paint a picture. Not hyperbole, not fear-mongering. Just a thought experiment based on what we know and what we suspect. A true Miyake-scale event arrives with minimal warning. Maybe a few hours of elevated solar wind. Maybe a fast CME that gives us 12 to 24 hours to prepare. Power companies start shedding load. Satellite operators safe mode their assets. Airlines reroute flights to avoid polar radiation exposure. Then it hits. Not all at once, but in waves. The magnetosphere compresses inside the orbit of GPS satellites, exposing the entire constellation to full solar wind. Half of them go into safe mode. A quarter suffer permanent damage. Navigation systems worldwide start glitching. Financial markets, which rely on GPS timing for high-frequency trading, freeze. Airlines ground flights because they can't navigate accurately. Ground-induced currents surge through power grids. Transformers fail. Not a few. Hundreds. Thousands. The grid fragments into islands, then collapses entirely in regions where spare transformers aren't available. Cities go dark. Not for hours, but for weeks. Months, in areas where transformer replacement requires manufacturing new units, a process that takes time and depends on functional supply chains. Communication satellites fail. Not all of them, but enough to degrade global connectivity. Internet backbone routes that depend on satellite uplinks go offline. Emergency services struggle to coordinate. Supply chains, already fragile, snap under the strain of cascading failures. And beneath all of this, the Earth itself responds. Telluric currents, stronger than anything in the modern instrumental record, flow through the crust. Fault zones already near failure get nudged. Earthquakes occur in clusters, not because the storm caused them, but because it triggered release of accumulated tectonic stress. Volcanic systems, sensitive to pressure changes and electromagnetic perturbations, show increased unrest. This isn't instant apocalypse. It's cascading degradation. Systems fail. Backup systems fail. Redundancies prove insufficient. The modern world, optimized for efficiency and just-in-time logistics, discovers that resilience was sacrificed for profit margins and convenience. Recovery takes years, not because the damage is irreparable, but because repairing it requires coordinated global effort, functional supply chains, and social stability, all of which are harder to maintain when large portions of critical infrastructure are offline. This scenario is not inevitable. It's not even the most likely outcome, but it's plausible. And plausibility should matter when the consequences are this severe. We don't need certainty to prepare. We need enough evidence of risk to justify building resilience into systems that currently have very little. The danger of historical amnesia is that we optimize for the disasters we remember and ignore the ones we've forgotten. We build earthquake codes based on the biggest quake in recent memory. We design flood defenses for the worst flood in recorded history. We plan for solar storms based on the Carrington event and the 1989 Quebec blackout. But what if those aren't the ceiling? What if the ceiling is a Miyake event, and we've simply never experienced one with modern technology? There's no countdown clock for rare events. They don't announce themselves. They don't give us decades of warning. They happen when conditions align, and alignment operates on planetary and stellar timescales that don't care about election cycles, quarterly earnings, or the next fiscal year's budget. The 12,000-year rhythm, if it exists, is based on geological and isotopic evidence from ice cores and tree rings. It's not prophecy. It's pattern recognition in data that spans millennia. And patterns, even imperfect ones, are useful if they help us prepare for possibilities we might otherwise ignore. We can't predict exactly when the next Miyake event will occur. We can't even say with certainty that one will occur in our lifetimes or our grandchildren's lifetimes. But we can say that the sun is capable of it, that Earth has experienced them before, that our magnetic shielding is weaker now than it's been in recent history, that our civilization is more vulnerable to electromagnetic disruption than at any point in human history, and that the January storm, as surprising as it was, might just be a preview. The question isn't whether we can prevent these events. We can't. Solar activity and geomagnetic field dynamics operate on scales far beyond human control. The question is whether we recognize the risk, take it seriously, and build systems resilient enough to survive and recover when the inevitable occurs. Because the alternative is waiting for hindsight. Waiting until after the grid fails and the satellites die, and the cascading failures teach us, too late, that we were measuring the wrong things all along. If the last reset happened before history was written, before we had cities and agriculture and electrical grids to lose, how would we recognize the first act this time? Would we notice the pattern before it completed? Or would we, like every civilization before us that vanished into myth and archaeological fragments, only understand what was happening in those final moments when understanding no longer matters? The storm has passed. The satellites survived. The grid held. But the questions remain, unanswered and increasingly urgent, hanging over us like a sword suspended by a thread we can't quite see, but know is fraying.